Okay, the third talk in this session is a fast and simple network. Fast and simple unbiased estimator for network reliability. And the talk is by David Carter.
Hi, thank you for coming. I'll dive right in. The network reliability problem is a classic problem where you're given an undirected graph and you assume that the edges of that graph fail independently with some probability p. Sorry, that should be a p. And then you ask about the probability, which I'll denote by UG of p, that the graph is disconnected by the resulting edge failures. And I'm going to be using these sort of standard parameters throughout the talk, and vertices, m edges, and minimum cut c. History. This problem's been around for a while and was in fact one of the first problems identified as a sharp p-hard problem, which of course means that it is at least as hard as NP-hard problems, and we're unlikely to find exact solutions for it. So the focus has been on a variety of approximation problems around it, and the most common one is to look for what's called an FPRAS, a fully polynomial randomized approximation scheme. It's parameterized by epsilon and delta. The goal is to return an approximation that is within 1 plus epsilon of the correct answer with a probability 1 minus delta at least. And you want to do this in time which is polynomial in n and in epsilon and in the log of 1 over delta. So back when I was much younger, I gave the first fully polynomial randomized approximation scheme for this problem, although actually it was for the unreliability problem. So that's the probability of disconnection. Reliability is generally talked about as the probability of being connected. And the problem is that when you do approximations, they don't necessarily match with each other, right? You can approximate one quite closely and be very far off from the other. Fortunately, given what we know, the unreliability problem is the one that actually matters in practice, because nobody really cares about a network that is completely unreliable. Right? So in general, you want to be studying networks that are quite reliable, where the unreliability is small, and that's where it's hard to approximate unreliability, and it's easy to approximate reliability. This first algorithm used some observations that only small cuts matter in the estimation of network reliability. It enumerated those small cuts, of which it showed there weren't too many, and then used DNF counting to estimate the probability that one of those cuts would fail. And the runtime of that algorithm was roughly n to the fifth. Although when we implement that I was able to prove, although when we implemented it experimentally, it seemed to show an order n cubed runtime. So interestingly enough, 20 years later, Harris and Srinivasan managed to prove a runtime of order n cubed. They didn't simply prove that this algorithm runs in n cubed time. They introduced a bunch of new techniques and ideas, and some inspiringly complex analysis. And I say inspiringly complex because it was looking at that paper which got me thinking about this problem again. I was sort of struggling to understand some bits of it, and that led me to think about some simpler ways to do things, which led to this work. So in this work, I'm going to show you a 7-line algorithm for approximating network reliability, and a 1-page proof for showing, or sorry, 1 paper page. It takes a few more slides than that to prove that it works. The algorithm is very straightforward, and the proof is self-contained, aside from one relatively well-known lemma. The runtime of this simple algorithm is order mn squared. If you then apply some pretty standard graph sparsification techniques, that lets you replace the m by n log n and get the running time down to n cubed log squared n. I'm not going to talk about the sparsification in this talk, both because it's standard and because I think it won't be needed once there are some further improvements in the primary algorithm. The background lemma, the one thing that you need to know that is in the paper, is about the sort of maximum and minimum reliability of a network. In particular, since the graph disconnects when the minimum cut fails, the probability of that happening is at least p to the c. That means the unreliability of the graph is at least p to the c. On the other hand, and this is much harder to prove, it turns out that no graph has an unreliability larger than n squared times that quantity. And more generally than that, the probability that the graph disconnects into k or more pieces as a result of the failures decreases exponentially in k, so long as this quantity, np to the c over 2, is smaller than 1. which you'll notice sort of matches up at it's sort of an interesting threshold for reliability. And the reason for this intuitively is that the cycle is the least reliable network for a given minimum cut. It has the fewest possible edges, the most minimum cuts, and furthermore, even after you contract some of those edges, it still has the fewest possible edges of any graph. So it has sort of the sparsest minors. And that means that it is the most likely network to fail. The cycle will disconnect if it's a minimum cut C cycle, then it has sort of edge groups of C over 2 edges between every pair of vertices on the cycle. And the graph will break into K pieces if K of those bundles of C over 2 edges all fail. And so there are at most n over n choose K bundles. They fail with this. Each one fails with this probability. So this is just a simple union bound. So that's the only thing that you need to know that isn't sort of presented in this work, although it's actually presented in an appendix in the paper, and I'll show it in an appendix of the talk if there's time at the end. So with that in mind, here is the entire algorithm for network reliability. If the failure probability is reasonably large, then you estimate it in the most obvious possible way, which is you run a bunch of experiments failing the edges and see how often the network disconnects. On the other hand, if the failure probability is small, you use this two-step procedure, where first you set this parameter Q to be at the threshold that I mentioned on the previous page. And that makes the graph more likely to disconnect to this threshold than at this small value P. Once you have that parameter Q, you generate an intermediate graph H by contracting all the edges with probability 1 minus Q. The other way to think about that is that you are deleting all of the edges of probability Q, which is too large. And this gives you a sparser graph than the graph that you're supposed to get. You then look at that sparser graph, which will have some pieces, and you compute the probability that that sparser graph ends up disconnected when you fail its edges that remain with a scaled probability P over Q. So that's the algorithm. The analysis involves a couple of claims. The first is that the graph H is so small that you can brute force the calculation of H's unreliability. The second piece of the argument is that both of these algorithms, the naive Monte Carlo algorithm and this more sophisticated one, produce unbiased estimators for the unreliability. And if you don't know what that is, I'll tell you in a minute. And both of those unbiased estimators have relative variance of n squared, which means that you only need order n squared of these experiments in order to get a close approximation to the correct answer, and this gives you your mn squared time algorithm. So that, at a high level, is the whole story. Is there any clock in this room? No? Okay, hold on. When am I finishing? Sorry, what's the finish time? Seven. Okay, so another 13. That's fine. Sorry, I should have thought of this sooner. Okay. So let's talk about the. Oops, did I skip it? Yeah. Okay. So here's the idea of an unbiased estimator. This is a general technique that you use to estimate some unknown quantity u. What you do is you define a random variable, capital U, whose expectation is the unknown quantity, and then you generate samples from the random variable. And of course, as you generate more and more samples, you'll converge on average to the unknown quantity u. The accuracy that you get by taking a single sample is determined by the variance of the sample, and we're going to be talking primarily about the relative variance, where you scale the variance by the square of the mean of the sample. And just a standard application of Chebyshev bounds tells you that you can sort of take down the variance, the relative variance, far enough to give you a close approximation by taking a number of samples which is roughly equal to the relative variance. Once you've done that, you get an approximation that is accurate to within epsilon with probability a quarter. If you do that log 1 over delta times and take the median, then you get an answer which is correct with high probability. And unbiased estimators, which I didn't know about when I was doing the original version of this paper, are, 20 years ago, are a wonderful way to do fully polynomial randomized approximation schemes. Because if you are sort of in the old-fashioned way of doing these approximation schemes, you sort of have to track your way through the epsilons and deltas all the way through the analysis. When you have an unbiased estimator, all you have to do is prove an expectation. Once you know the expectation, you're done. You just tack on the epsilon and delta next to the total number of experiments that you need, and you have your epsilon delta approximation. So let's take this idea of relative variance first, thinking about basic Monte Carlo sampling. So here, you want to estimate the probability of this event, and so the way you do it is you sample from your sample space and you see if the event happened. So you have an indicator variable for this event, which is 1 if it happens, and the expectation of this indicator variable is equal to the probability of the event. Since it's an indicator variable, its variance is very easy to compute, and actually I'm just going to look at the expectation of the square, which is an upper bound on the variance, and that is u. On the other hand, the square of the mean is u squared, so when I divide them, I get a relative variance of 1 over u, which tells me that 1 over u samples suffice to perform the estimate. You'll notice you can't really hope to do better, because I expect to need 1 over u samples just in order to see any occurrences of the event, and until I see one, my estimate's going to be 0, which is obviously not a good estimate. So we can apply this idea to network reliability by doing naive Monte Carlo sampling. We simply flip coins for each edge, make a failed graph, and see if the graph has become disconnected. This exactly matches the previous discussion, where the probability of the indicator variable is ug of p. And so that means I need 1 over ug of p samples in order to estimate reliability effectively this way. And in particular, since I can obviously construct each sample in order m time, it's going to be an order mn squared time algorithm, so long as the unreliability is sufficiently large. It needs to be bigger than than 1 over n squared. Now, since the graph has minimum cut c, as I argued before, the unreliability is at least p to the c, so it is sufficient for p to the c to be larger than 1 over n squared in order to allow me to use this algorithm. So what we really have to do all our work on is in the case where p to the c is less than 1 over n squared. Okay, because in this case, even that a single min cut might not fail at all, and so we won't see anything. So the solution to this problem is an idea that's sort of generally called importance sampling. There's this event I'm interested in. It's not very likely. So what I'm going to do is I'm going to sample from a different distribution which focuses on the event that I care about and makes it more likely. Now, of course, since I am now making failures more likely, that's going to throw off my estimate. So in order to fix this, I'm just going to scale my estimate back to cancel out the likelihood change that I introduced by changing my distribution. So a very simple example of this would be a coin flip, where I have a coin that's very biased. It comes up with a very rare probability p of heads. So if I want to estimate p, what I can do is I can use a coin whose heads probability is q, which is much larger than p. And in order to balance out my shift in the bias, when I get a heads, I won't return 1. I'll return p divided by q. So you can now see that the expected value of this new experiment is still p. It's the same expected value as the original coin. However, the variance is now that with probability q, I will get p over q squared. So the variance is now p squared over q, which means that the relative variance is no longer 1 over p. Now it's 1 over q. So I only need 1 over q samples instead of 1 over p samples, and I can estimate faster. So we're going to apply the same idea in reliability. We've already covered the case of p to the c larger than n to the minus 2. So in the case where p is small, I'm going to set q at this threshold value. I'm going to delete edges with probability q. So this is going to make it reasonably likely for a min cut to fail. So I will see some occurrences of these failed networks that I need to estimate. The question is, how do I rescale the disconnection events to give me a proper estimate for the original network's unreliability? So in order to do that, I'm going to take a slightly different perspective. I'm going to think of this construction as a two-step process for constructing a sample of p failures. First, I set my threshold, and then I weaken all of the edges with this probability q. I then delete only the weakened edges, and I delete them with probability p over q. I then declare a disconnection if the resulting graph is disconnected. So you can see that since the way I delete an edge is first by weakening it with probability q, and then by deleting it with probability p over q, so each edge is deleted with probability p. In other words, this is producing a sample of the correct graph. However, since I only delete weak edges, after the first step, I can contract all of the non-weak edges. And that gives me a graph H. And G will only be disconnected if H is disconnected by the failure of its weak edges. So what I've just shown is that the unreliability of the original graph at edge failure probability P, which is just the expectation of the disconnection event, I can look at that by conditioning over the graph H that I generate in the first step. And that tells me that the disconnection probability for P is just the expected value of the disconnection probability of H when I compute it at this alternative failure probability. In other words, this quantity, UH of P over Q, is an unbiased estimator for the quantity that I want to compute. Whoops. So that's the summary. We now have an unbiased estimator. Two questions remain. How do we compute it? And how do we show that its variance is small so that we can know that we don't need to take too many samples? So here's the analysis. Recall, I said at the beginning that the cycle is the least reliable network, which means that every network has unreliability at least P to the C because the min-cut might fail, but that no network has failure probability more than n squared P to the C, and this is the maximum probability of breaking into K components. So I'm going to sort of store some of these things we need to remember up at the top and draw some conclusions. So remember, we're building H with probability n to the minus 2. So I can conclude from the bound on the number of components that if I plug in k equals log n, the probability that I have log n or more components is tiny. That is, with high probability, the size of this graph H is only log n. But that's great. If the size of the graph H is log n, then I can compute that unreliability by brute force in exponential time. And it will only take me polynomial time. Also, because the graph is so small, I can use the deterministic upper bound on its reliability and conclude that the unreliability of H is at most this quantity. So it's the size of H squared times the failure probability to the C. But remember that we set Q to the C to be equal to 1 over n squared. So I pull that up, and I get nh squared times P to the C. And since H is small, this is roughly n squared P to the C with high probability. So let's use that fact in order to analyze the relative variance of this estimator. That's equal to the expectation of the square divided by the square of the expectation. Now I'm going to play this trick where I'm looking at the expectation of the square. I'm going to take one of the two terms that's being squared and replace it by this upper bound. So I put n log n squared P to the C in instead of UH of P over Q. And so I have this product. Now it's a constant, so I can pull it out from the expectation and be left with this quantity over here. Now you notice that I have an expectation above and a similar one below. But we already said that this is an unbiased estimator for the unreliability. So this expectation is precisely the unreliability of G. So I have the unreliability of G squared in the numerator, one unreliability in the numerator, squared in the denominator. I cancel things out. The other thing that I now need to notice is that the unreliability is bigger than P to the C because the min-cut can fail. So this P to the C is canceled by the second copy of the unreliability in the denominator, and I end up with an n log n squared variance. That's the end. Okay. Now, I cheated a little bit because I made an assumption. I asserted something was true with high probability, and then I assumed that it was always true by looking at this, by treating it as a constant in the expectation. It's not actually that big a deal. If we look at this rare case where H is large, well, even if H is large, still H has size less than or equal to n, so I can get a decent bound on the unreliability of H. And this likelihood is really small, so it contributes negligibly to the overall relative variance. All right, so that's the end, right? We brute forced the computation of UH of P over C, P over Q. It has a small relative variance. Thus, we have a fully polynomial randomized approximation scheme for the unreliability. All right, but what's the polynomial? Up here I said brute force is polynomial time with high probability. But you have to go look at the constants in order to see what polynomial it is. Maybe it's n to the 23. All right, let's fix that. We'll just use the algorithm we just developed in order to compute UH of P over Q. right? So we no longer need to use a brute force algorithm. Now we have an algorithm with a polynomial runtime. It's being run on a graph of size log n. So maybe it takes time log n to the 23rd. Who cares? That's still dominated by the linear time it takes to construct the sample. And you have to do a little work to show that the relative variance is composed properly, but it's straightforward. Is there anything I want to say here? Yeah, so the result, the main result of the paper, is that you get relative variance of n log n squared in order m time, and so you get your fprass in mn squared time. The paper cleans up some of the logs by being a little more careful than I've been in this talk, and it also shows the argument I just gave you was that this is a high probability result, but it turns out you can make it work this way in expected order mn squared time as well. A couple of extensions in the paper. First of all, I show how you can use sparsification in order to solve the problem more quickly, replacing m by n. And I also show that you can use this technique not only to estimate the unreliability, but also to generate a failed graph from the proper distribution. So if you want a sample of G conditioned on its being failed, you can use the techniques that are described here in the same sort of two-step sampling process in order to do that construction. So I want to finish with a very brief discussion. What our analysis actually proved was this bound on the relative variance. There's an h squared term in the numerator, which we showed was very small, and there's an unreliability of G term in the denominator, which we used to cancel the P term in the numerator. But actually, let's consider the cycle. It's the least reliable graph. Its unreliability is actually n squared P to the C. It's a factor n squared bigger than our pessimistic assumption, which means we get a relative variance of order 1 on the cycle, and we only need a constant number of trials. If we instead consider the dumbbell, which is 2 cliques connected by C edges, this is the most reliable graph with minimum cut C. So it doesn't give us anything in the denominator. However, we can use a different value of Q. We can set Q equal to 1/2, and we still get a tiny h. So in that case, our relative variance is also roughly 1. So in both these cases, the least reliable and the most reliable graph, we can achieve a relative variance of 1 instead of a relative variance of n squared. And that gives us a linear time for fprass in both cases. So I'm going to finish up with some conjectures that follow from this. First of all, that in fact, the biggest relative variance, the most confusing graph, is actually that dumbbell, because it only has one minimum cut, and adding more cuts is just going to smooth out the sampling and reduce the variance. And if that is true, then you can get an order n squared time fully polynomial randomization technique using some recursion. My second conjecture is even more fun, which is that for any graph, you can find a suitable Q that gives you a relative variance that is constant, in which case you would get a linear time approximation algorithm for network reliability, which would be awesome. So that's the conclusion. I gave the first unbiased estimator for network unreliability. I gave a short, simple, self-contained proof of its correctness that suggests a pretty small constant factor, and so it yields the fastest known fprass. I gave a generator for disconnected graph, and I presented you with a pair of conjectures. The first suggests a quadratic time algorithm, which would already be a nice improvement, and one that doesn't require sparsification, which is why I didn't talk about it. I have about root 1/2 of a proof, of which I am root 1/2 confident in. If I ever have a chance to write it down, that will go up. I don't know anything about conjecture 2, and I'm really excited about it because it would be a linear time algorithm. Thanks very much. Yeah. Yeah, so again, this is one of the wonderful things about unbiased estimators, right? The prior algorithms sort of did various kinds of arguments about how if I throw away these cuts, it only introduces an epsilon here and an epsilon squared there, so on and so forth. So I frankly don't recall the epsilon dependence of my first algorithm, and I couldn't figure out the exact epsilon dependence of the Harris algorithm, except to know that it's polynomial. This algorithm, you just tack the epsilon on the outside, so it's just the one that comes from Chebyshev's bound, so it's a 1/epsilon squared bound, just as any normal sampling experiment would produce.